Hey everyone, welcome to this explainer on Unit 3, covering factoring methods and array techniques. Now, if you're a first semester BCA student, you might hear the word algorithms and immediately picture pages of dense, abstract, super intimidating math. But today, we're going to completely reframe that. I want you to think of algorithms not as some abstract theory, but as a friendly, totally accessible toolbox. We're going to be looking at small, highly reusable techniques that you can pick up and use right away.
So, here's our game plan for today. First, we'll open up your new algorithmic toolbox. Then, we'll dig into 5 factoring methods, followed by 7 array techniques. And finally, we'll wrap up by looking at why partitioning matters most.
All right, let's jump right into Part 1, your new algorithmic toolbox.
Think about where you're at right now. You already know your basic C syntax, right? You've got loops, variables, and data types down. Honestly, that means the hardest part of learning the language grammar is totally behind you. All you need now are the actual problem-solving tools to start building real things. You've got the hammer and the nails, so to speak. Now it's time to learn how to build the frame.
Moving on to Part 2, let's explore 5 factoring methods. Let's slide open that first drawer of our toolbox. Inside, we've got 5 tools for manipulating single numbers. The first one? Finding the square root of a number without relying on a built-in library function. It's so cool because it basically just mimics human guesswork, only way faster. Say we want the square root of 50. We take an initial guess, maybe half of it, so 25. That's obviously way too high, so we just average our guess with 50 divided by our guess. We average 25 and 2, which gives us 13.5. We repeat that loop again and again, rapidly closing in on the true answer. In literally just a few quick steps, this repeated averaging homes right in on 7.07. It's basically a method of continuous improvement.
Now let's check out our second and third tools, which are sort of siblings. Tool 2 is finding the smallest divisor of a number. Take 91. Is it divisible by 2? Nope. 3, 4, 5, 6? No luck. But we hit 7 and boom, 0 remainder. So 7 is our smallest divisor, meaning 91 is simply 7 times 13. Now, Tool 3 takes that exact same logic but puts it on a loop to find prime factors. To break down the number 60, we find its smallest divisor, 2, which leaves 30. Divide by 2 again, leaving 15. Then we divide by 3, leaving 5. We just keep carving off the smallest piece until all we've got left are prime building blocks, 2, 2, 3, and 5.
Tool 4 is an absolute classic, Euclid's method for finding the greatest common divisor, or GCD. Let's look at 48 and 18. Instead of agonizing over all the factors of both numbers, we just use repeated division. 48 divided by 18 leaves a remainder of 12. We shift our focus over and divide 18 by that remainder, 12. Which leaves 6. Finally, 12 divided by 6 leaves a remainder of 0. The exact moment that remainder hits 0, our last divisor, which is 6, is our greatest common divisor. It's beautifully elegant and incredibly fast.
The whole point here is that a great algorithm saves you precious time, and Tool 5 really nails this. Say you want to raise a number to a massive power, like 3 to the power of 13. The naive way is to just multiply 3 by itself 13 times. That's 13 separate, tedious steps. But our power tool here is something called repeated squaring. By squaring our base and halving our exponent whenever we can, we get the exact same result in only 4 steps. When numbers get huge, that kind of efficiency is a total game changer.
Okay, let's shift gears to Part 3, 7 array techniques.
It's time to open up the second drawer of our toolbox. This one is all about handling collections of numbers. To keep things super clear, we'll use a constant companion for this section, a simple array representing 5 student marks. The marks are 42, 78, 55, 91, and 63. We're going to run this exact same data through several different tools so you can see exactly how they operate.
Tool number 1 in this drawer is array order reversal. If we want to flip this array backwards, we definitely don't create a whole second array. That's just a waste of memory. Instead, we reverse it in place. We take the very first element, 42, and swap it with the last one, 63. Then we step inward, swapping 78 with 91. That middle element, 55, just stays right where it is. 2 quick swaps, and the whole array is flipped.
Let's think about a real-world scenario to introduce our next 2 scanning tools. Looking at this little class of 5 students, you'd probably want to know right away which one is the highest mark, and how many students scored above the class average.
To answer that first question, we pull out our maximum finding tool. We scan through the array from left to right, basically keeping a running best so far number in our pocket. We see 42,
then 78 takes the lead, then 91 jumps ahead. 63 comes along, but it can't beat it, so 91 is our absolute max. Using very similar logic for our third tool, we can compute the class average, then do one more linear scan to count exactly how many individual elements actually surpass that average. It's so straightforward.
We also keep a couple of highly specialized tools in this drawer. Tool 4 lets us strip out duplicate values in a single pass. But the catch here is that it only works if the array is already sorted, because that guarantees any duplicates are sitting right next to each other. Then there's Tool 7, which scales our array logic up into 2 dimensions. It uses a really clever triple-nested loop to actually multiply 2 small matrices together.
Moving on to our final section, why partitioning matters most.
We've covered a bunch of awesome tools, but there's one array technique that seriously deserves its own pedestal. To really get this power tool, we have to understand the term pivot. A pivot is simply an anchor point. It's a value we choose from our array that acts as a divider, partitioning the whole collection into 2 distinct halves.
Let's see this in action using our trusty marks array. If we pick the last number, 63, as our pivot, our algorithm sweeps through the array. It neatly shifts all the numbers smaller than 63, which are 42 and 55, over to the left side. Then it shoves all the larger numbers, 78 and 91, over to the right. Finally, it drops our pivot, 63, smack in the center. The left side isn't fully sorted, and the right side isn't fully sorted either. But that 63? It is locked perfectly into its forever home.
This perfectly highlights why partitioning is such a big deal. Because that pivot always lands in its final absolute sorted position, we actually get our 6th array tool totally for free, finding the kth smallest element. Think about it. If you need the 3rd smallest number in some massive array, you don't have to waste time sorting the whole thing. You just partition it. If your pivot lands in the 3rd slot, boom, you're instantly done. If it lands in the 5th slot, you know your target has to be in that smaller left pile, and you can completely ignore the entire right side.
So why does partitioning truly matter the most? Well, I want to build a little hype for Unit 4 here. Partitioning is actually the raw, unmodified engine behind quicksort, which is one of the most famous and efficient sorting algorithms on the planet. By learning to partition an array today, you are actually learning the secret beating heart of the complex sorting you'll be doing tomorrow.
And that wraps up our explainer. Look, every massive, mind-bending program you will ever write, or even use, is really just a clever combination of these small, totally manageable toolbox techniques. You've already got the syntax down, and now you're building out your toolkit. So I'll leave you with this. Which simple tool are you going to combine first to build your next complex program? Keep experimenting, and happy coding.